So today we are going to be starting with some AS level chemistry past papers of chemical energetics. So let's get started. They're going to be a little difficult, a little tricky, but no worries. We're going to solve them all. I'm going to explain all concepts to you guys, and you guys are going to be crystal clear about chemical energetics. It's going to be on your fingertips. Okay, so let's start and try to do as many questions as possible. Which equation has an enthalpy change equal to the standard enthalpy of formation of sodium oxide? Okay, so now there's a very important word over here, and these options A, B, C, D, I'll tell you. This is my something that I myself have experienced it. That when you read all these options, all of them seem correct. Honestly, all of them are gonna seem correct to you, but you have to first visualize what they're asking. You have to find the standard enthalpy of formation of sodium oxide. So what is enthalpy of formation? Enthalpy of formation is that your 1 mole compound 1 mole compound should be formed. Okay, so you are forming 1 mole of compound. So on the basis of this thing, we can eliminate option D. Why? Because we're forming 2 moles. Okay, first thing is done, and we can eliminate option A as well because we're forming half mole. So now we're just left with two options, option B and option C. Now the second part says that from its elements, okay, both of them, they are formed from the elements. Good. In their standard state, this means the element should be in their standard state. And what is standard state? Their state at room condition. In their standard state, okay, sodium, the standard state of sodium is a solid. So that's good to go. It's a solid, and the standard state of oxygen is a gas. So in both, the elements are in their standard state. So 1 mole of compound should be formed from its elements in their standard state under standard conditions. That means at room temperature, at 298 Kelvin. 298 Kelvin is your room temperature under standard conditions. Achha. Now you guys have to look for the correct option on the basis of balancing the equation. Okay, so now this is Na2O. Okay, so we have 2 oxygens over here and we have 1 oxygen over here. So this is incorrectly balanced, hence making option number C the correct option, because this is correctly balanced. Moving on to the next question, which says the Boltzmann distribution of the hydrogenation of an alkene. Okay, so you're hydrogenating an alkene. That means you're adding hydrogen to an alkene. And what happens when you add hydrogen to an alkene? What do? You convert an alkene into an alkane at a particular temperature in the absence of a catalyst is shown. Okay, this is the graph in the absence of catalyst. Absence of catalyst. What does absence of catalyst mean? That your activation energy is going to be higher, and if there is catalyst added, the activation energy is going to move back, and it's gonna move back. So which row correctly describes the effects of adding a nickel catalyst to the reaction vessel? So what will happen? This arrow that is right now over here is gonna move backwards, so it's gonna be probably somewhere here. So the shape of the Boltzmann distribution, it's not gonna change. What you are not changing this curve remains the same. This curve will not change. What will happen is this activation energy is just gonna move backwards and gonna decrease. So the shape of the Boltzmann curve is only changed by one thing. Only one thing can change this. What's that one thing? Temperature. If you increase or decrease temperature, it's gonna affect the shape of the Boltzmann curve. So now it does not change, and the activation energy is gonna decrease because it's gonna move backwards, making option C the correct one. I hope you understand it. Okay, next part says an energy cycle is shown. Okay, what kind of cycle is this? This is a particular example of a very beautiful Hess cycle. Chemistry is such a lovely subject. I don't know why you guys feel it's difficult, or I just don't get it when people say it's difficult. It's easy as ABC. Okay, so this is a Hess cycle. That's been wrong. The energy changes involved are X, Y, and Z. Okay, so let's analyze each one what's happening is that we have methane and we've added oxygen to it. Okay, we have methane and we added oxygen to it. What's going to happen when you're going to have methane and add oxygen to it? Obviously, it's going to combust. There's going to combustion happen. And what are the products of combustion? Carbon dioxide and water. Good to go. Now, what's happening over here? That this methane is being broken down into its elements, the elements from which it is made: carbon, hydrogen, and oxygen. So, methane broken down into elements, these elements are then forming carbon dioxide and water, and methane being combusted to form carbon dioxide and water. So, all the arrows are pointing towards this side, carbon dioxide and water. Okay, so just let's read the question. The numerical value of the energy change Y is either negative 890 or positive 890. Okay, now this should be crystal clear to you guys. This is methane, this is oxygen, and this is carbon dioxide and water. What's happening? What kind of reaction is occurring at Y? I don't think there should be even a pinch of confusion in it that combustion is happening at Y. So your combustion is occurring. Combustion is a prime example of exothermic reactions. Combustion reactions are always exothermic. You always release heat when you combust something. So what's going to happen is that heat's going to be released. So it cannot be plus 890. It has to be negative 890. So let's write in negative 890 over here. Okay, next part says the numerical value of energy change Z is either negative 964. Okay, this is Z. Okay, either it's negative 964 or positive 964. Okay, let's analyze what's happening at Z. So there are some bonds that are being broken and there are bonds that are being formed. It's formation happening. And formation is majority times exothermic. Okay? Majority times it's exothermic, but it can be endo as well. Okay, which of the three values are negative? Okay, which of the three values are negative? We are sure about the first value, that's going to be Y. Y. Okay, we have two options. Now we have to figure out either Z is going to be exo or endo. Okay, for that you need to know one thing. X, I don't care. I just don't care. And if you see towards one thing, what's happening at X is that bonds are being broken. And when bonds are being broken, these carbon, hydrogen in methane, these bonds are being broken. And when you break bonds, it's always endothermic. So this one's going to be positive. X is going to be positive, but Z is going to be negative. Why? Because bonds are being formed. You're forming a proper compound, carbon dioxide and water. I know, you might think that this H and H bond is being broken. Yeah, it's being broken, but the enthalpy, the total enthalpy, these two bonds are being broken. This oxygen, double bond oxygen, and hydrogen bond, it's been broken, I agree. But you are forming these many bonds. Look at it. You are forming two waters. So don't you think after combining the energy of this bond, this bond, this bond, this bond, this bond, this bond, obviously it's going to overpower the energy that you are using over here to just break them. So definitely Z is also going to be negative, and I'm pretty sure about it. So it's going to be option C. Why? Because bonds formed here, and why? Because this is a exothermic reaction. So we are done with this question as well. These are, by the way, very recent past paper questions, like 2024 and that stuff. Gas Q decomposes slowly at room temperature. Okay, it's decomposing slowly at room temperature. Okay, gas Q. This is Q. It's converting into X and Z. The Boltzmann distribution curve for gas Q at room temperature is shown. Okay, these are the number of particles. This is the molecular energy. This is the activation energy. Which change occurs when a catalyst is added to gas Q? That's so easy. This activation energy is going to move backwards. So the peak of the curve moves to the right to the diagram. Always remember, catalyst cannot affect the shape of a Boltzmann curve. Write it down somewhere if you don't remember. Catalyst does not affect the shape of a Boltzmann curve. Because what catalyst does is simply decrease the activation energy. So catalyst is not going to do this. The number of particles with enough energy to decompose increase. Okay, we're going to see towards it. First, let's read all the statement. The kinetic energy of the unreacted particles increases. Catalyst does not increase the kinetic energy. I just don't know why people just don't get the concept of catalyst the first time. Dekho, this is the energy of the particles. Catalyst is not going to do anything with the energy. The energy of the particles remain the same. It just decreases the passing marks. Okay? For instance, your class, you have a class test. Okay? You have a class test. And the people in your class, out of 50, one got 30, one got 36, one got 40, one got 25, one got 28. The passing marks for your class is one got 45. The passing marks for your class is 50 out of 40. If anyone got a 40, that girl is going to be passed. 40 or above. So how many girls or boys are going to pass? Only 2 people are going to pass. This person and this person. Only 2 people are going to pass if the passing marks are 40. But what a catalyst does is, a catalyst decreases the passing marks. It decreases the passing marks to, for instance, 30. Now the passing marks are 30. Now how many people will pass? This 40, this 45, this 36 and this 30. Now 4 people will pass the test. Before that, 40 people were passing the test. 2 people were passing the test when 40 was the passing marks. Catalyst lowered the passing marks. It did not change the marks of the people. The marks are still the same: 28, 30, 36, 40, 45, 45, 40, 25, 45. What it did was it decreased the passing marks. So more children in the class could pass the test. Do you get it? What's happening when you add a catalyst? You're not increasing the energy, you're just decreasing the activation energy, decreasing the passing marks. So I hope you get it. So that's going to be absolutely wrong. The value of the EA decreases, moving the vertical dotted line to the right of the diagram. This is the right side. No, if it moves to the right, that means it's increasing. It should move towards the left of the diagram. We'll cross out this as well. Now I'll tell you why option B is correct. The number of particles with enough energy to decompose increases. What's happening is decomposition. Okay? Now, since the activation energy moves backwards, initially only these particles were reacting. Now these green ones are also going to react. So the number of particles that had enough energy to decompose initially was only this part of the triangle, only this triangle, but now it increased to this triangle. So now more particles can decompose. I hope you get it. Moving on to another very latest past paper question, which says that the volume of ammonia produced against time is measured in 2 experiments. Okay, you should know this is an exothermic experiment. In experiment 1, 3 mole of H2, 1 mole of N2 react together 45 degrees Celsius in a pressure of 200 atm. The graph showing the volume of ammonia produced against time is plotted. Experiment 2 is then performed. Experiment 2 differs from experiment 1 in one condition only. Okay, so initially we performed experiment called experiment 1, and then we performed an experiment called experiment 2. In experiment 2, firstly the rate is slower or faster. I'd like to know, is the rate slower or faster? That's going to be our test. If you guys think you know it very well, tell me, is the rate going to be faster or slower in experiment 2? It's going to be faster. In experiment 2, you have a steeper gradient. In experiment 1, you have a less steep gradient. So write it with experiment 2, faster initial rate. Don't look at the line, don't look at the product. Product might be less, but the rate is faster. There's a difference between product and rate. So faster initial rate is going to be for experiment 2. Faster initial rate. And for experiment 1, it's going to be a slower initial rate. But, for For experiment 1, we're forming more product. So the moles of the limiting reactant is more. I just write this line and I love this line, and I just want all my students or anyone listening to me to learn this line. That the moles of product, just write it down somewhere if you want to learn chemistry. The moles of product depends on the moles of limiting reactant. Depends on the moles of limiting reactant. If you increase the moles of the limiting reactant, the product increases. So product and limiting reactant, they have a good direct relation, but the excess and the and the product, they don't have any relation of the limiting reactant. So don't try to increase excess and say that your products can increase. Acha. So now we have 3 mole of H2, 1 mole of N2. This is the temperature. Okay. For experiment 2, and this is the pressure. We need a faster rate. So what we're going to do is, an iron catalyst is present in experiment 2. I agree that a catalyst could be present and that would increase the rate, but why is the product decreasing? That's my concern. I say, okay, I know that a catalyst is there, that is why it has more rate, but why is the product decreasing? I need an explanation for that as well. So I'm going to read the other statements as well. 2 mole of helium gas is present in the reaction mixture in experiment 2. But helium is useless gas. I have nothing to do. I want nitrogen, I want hydrogen, and I want ammonia to do with this graph. Helium has nothing to do, so I just don't care about helium. A pressure of 250 atm is used in experiment 2. A temperature of 600 degrees Celsius is used in experiment 2. Okay, so now volume of NH3. What do you think? What's gonna be correct? There are two statements. Both would increase the rate. A pressure of 250 atm would definitely increase the rate. Initially you were doing it at 200, a 250 would increase the rate, and initially you were doing it 45, so 600 would also increase your rate. But you need to keep one thing in mind. You know what? I tell you what. How many moles do you have on this side? On the left side you have 4 moles, right? You have 4 moles on this side and you have 2 moles on this side. So if you increase the pressure, equilibrium will try to decrease it, and equilibrium will move forward to decrease it. And the product is gonna increase. But if you increase the temperature, equilibrium is gonna move backward and the product, it's gonna decrease. Why? Because this is a exothermic reaction. So equilibrium, if you increase the temperature to 600, equilibrium in trying to decrease it will not do the forward reaction, would increase the backward reaction. So now all the conditions are in front of you. And you know one thing for sure, that in experiment 2 the yield decreases. So ammonia decreases if you increase the temperature, because if you increase the pressure, equilibrium moves towards the right, so ammonia would increase. But over here we see ammonia decreases, so temperature has been increased. That's why ammonia decreases, but the rate increases because of the increase in temperature, which makes option D the correct answer. I know this was a tricky one, but you had to think 2-3 different ways. Okay, the next one says that W volumes of HNO2 undergoes dispropagation reaction to produce U moles of HNO3. I guess this is more concerned towards the redox thing, so let's skip it. In high temperature of car engines, nitrogen reacts with oxygen to produce nitrogen monoxide. We know this reaction. The reaction has an activation energy E, so endothermic reaction. So which reaction pathway diagrams can we just cross out? The exo ones, in which the products are going to be lower than the reactants. So only this is crossed out. This is exo. Okay, now plus 90 is gonna be the enthalpy change. So enthalpy change should be from the reactants to the product above. So this is for an exo. Okay, so now what's the difference? The activation energy for an endothermic reaction is from the reactants to the top. This is from the products to the top. That's incorrect. So it's gonna be option C. This was easy. The apparatus used to determine the value of enthalpy of combustion of butane 1-ol is shown. The mass of 100 1.00 cm cube is 1 gram. Okay, we have 175 cm cube of water. We have a thermometer dipped. We have a copper can. Copper is a very good conductor, so you know one thing, that what's going to happen, heat is going to be lost from the container. So this is not a advisable apparatus for measuring the enthalpy change, I'd say. Okay, initial mass of the burner. This is initial temperature of water is this. Final mass of burner plus butane 1-ol. Okay, so this is how many grams of butane 1-ol is used, and final temperature of water is this. Okay, firstly we need to find the enthalpy change. That's going to be Q equals to mc delta T. Okay, you should know Q equals to mc delta T. Q is going to be your enthalpy change, mass of water that you are using. You have 175 cm cube. 1 cm cube equals to 1 gram. 1 cm cube equals to 1 gram. So 175 cm cube is going to be equal to 175 grams. So mass is going to be 175 multiplied by the C is the specific heat capacity of water. So you should know that it has a fixed value, the specific heat capacity of water. So it's going to be given to you in the exam. So specific heat capacity of water, you don't need to learn it, it's going to be given. It is 4.18 joules per kilogram. So this is going to be 4.18 multiplied by the change in temperature, but the change in temperature has to be in Kelvin. This is in degrees Celsius, but obviously when you convert both 273 you add and convert them into Kelvin, the change in temperature comes out to be the same. In degrees Celsius and Kelvin, the change comes out to be the same. That does not mean Kelvin and degrees Celsius are same. But if you are comfortable, first convert and then find out the change. But I know the change is same, so I'm going to put 41.1 minus 17.6. And I'm going to plug this entire thing into my calculator and find out the value. 175 multiplied by 4.18 multiplied by 41.1 minus 17.6, and this gives me a value of 17190.25 joules. Now what do? I find out the moles of butane 1-ol. Why do I find the moles of butane 1-ol? Because I have to divide it by those moles, because I need the enthalpy change for combustion of butanol. I need to burn 1 mole of butanol. So this is the MR of butanol. What's going to be the mass of butanol used? This is the initial mass of the burner plus butanol. This is the final mass of the burner plus butanol. We cancel the mass of the burner. So initial mass of butanol and after burning the mass of butanol. So let's figure out. That's going to be 58.34 minus 57.85. 58.34 minus 57.85. So this is gonna be 0.49 grams of butanol. We're gonna divide it by MR, mass divided by MR, which is 74, is gonna give me the moles of my butanol, which comes out to be 0.006621621 moles. Okay, these are my moles. Now I divide my enthalpy change with my number of moles. Why? because I need the enthalpy of combustion of 1 mole. This is for these many moles, so I divided the enthalpy by the number of moles, so I get for 1 mole. Okay, so this divided by 0.00662162. I hope that I remember it. Okay, so it's gonna be 17110.25 divided by my answer, which gives me a very large number, a very large number, which I'm gonna divide by 1000 to convert it into kilojoules. So I get 2583 kilojoules per mole. And this, if I round it off to two significant figures, is 2600 kilojoules per mole. Rounding off, yeah, rounding off to two significant figures. Why? Because all the data is almost to three significant figures, but the answers are in this answer is, I guess, up to two significant figures. So this is what my answer is coming out. Okay, the next part says that in the diagram, X is the Boltzmann distribution for the energies of the particles in a reaction, and EA1 is the activation energy of the reaction. Okay, so this is a very interesting question. We have a lot of Boltzmann curves drawn. This one, and this one. And EA1 is the enthalpy change for the reaction. Okay, ठीक है. EA1 is the enthalpy change for the reaction. Which statement is correct? EA2, this is EA2, is the activation energy at a higher temperature. Always remember, temperature cannot change the activation energy for a reaction. Just write it down somewhere that temperature cannot change the activation energy. Cannot change. These are golden tips. Okay, these are golden tips that I am giving you for your exam. On 13th November, you guys have your AS level P1 exam. These are golden tips. Temperature cannot change what can temperature not change? The activation energy. So temperature cannot change your activation energy, which is EA. What can change? Catalyst can only change it. Catalyst can alter EA. Okay, so this option is ruled out. EA2 is the activation energy at a lower temperature. Cross. Why is the Boltzmann distribution at a lower temperature? So what's gonna happen? Y, where is Y? Okay, when you lower the temperature, firstly the peak should increase. So let's see, Y has a higher peak. Very good. The peak should increase and the curve should shift towards your left side. Both conditions are fulfilled. So I think it's going to be C, but don't just be too quick with it. You have to read all the options. Okay, don't be quick with it. Read all the options. Z is the Boltzmann distribution at a higher temperature. Z cannot be the Boltzmann at a higher temperature. Do you know why? There's a problem with it. There's a very big problem with it. If Z is the Boltzmann distribution at higher temperature, the level of this peak should be lower. The level of this peak should be lower than X. X is the original, and at lower temperature it should be something like this. There should be a drop in the peak height. There's no drop. It's even higher than this. That's incorrect. For a higher temperature, the peak height decreases, and for a lower temperature, the peak height increases. So this is completely incorrect. Moving on. Okay, now we have to do a lot of calculations. Okay, ethane can react with chlorine to produce 1,2-difluoroethane. That is what we know after studying organic. This is the enthalpy change. What is the bond energy of this CF bond in 1,2-difluoroethane? Okay, a very good question. So now we have to draw the bonds. I'd highly recommend you guys to draw all the bonds. So first, let's draw C2H6. This is gonna be a difficult question. This used to come in O levels, and that was easy one, but this is difficult. Okay, C2H6. Okay, be patient. Be humble, and just don't be intimidated by it. Okay, plus F2. F2 like this, but there are two F2, so we're gonna make one more like this. Okay, so these are the reactants. So now we are gonna circle them like this, and I'm gonna write these are my reactants. Okay, now I'm gonna see all the bonds in my product. C2H4F2. Okay, C2H4. Okay, H4 and F2 like this. Plus, what's my other product? C2H4F2 and 2HF. Plus 2HF. 1HF and 2HF. This is such a easy reaction, but it is a little trickier if you guys don't pay attention at the bonds, if you don't draw them correctly. Otherwise, it's an easy reaction. These are my products. I have my reactants, I have my products. So let's now calculate the enthalpy changes. Firstly, I'm going to calculate all the enthalpy change for all the bonds that are being broken down in my reactants. Okay, so how many CH bonds do I have? I have one CC bond in my reactant. So I'm gonna write one carbon. Plus I have how many carbon hydrogen bonds? 1 carbon hydrogen, 2 carbon hydrogen, 3 carbon hydrogen, 4 carbon hydrogen, 5 carbon hydrogen, 6 CH bonds. 6 CH bonds. I hope I make myself clear. Please don't mess this up. 6 CH bonds. Plus, you can see this is quite clear. There are 1 and 2 FF bonds. So there are 2 FF bonds. So now let's calculate the enthalpy for all of them. So 1 CH. So 1 multiplied by, what's a CC bond? 1 CC bond. A CC bond is a 350. So 1 multiplied by 350. Plus 6 multiplied by CH. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Be sure about it, because once it's done 410. So 6 multiplied by 410. Plus 2 multiplied by FF. 158. So 2 multiplied by 158. Done. All the energy that's going to be required for my bonds to break. Let me calculate. 350 plus 6 times 410 plus 2 times 158, and that gives me 3126. So that's all the energy that's going to be absorbed in for breaking these bonds. So now in the product, bonds are going to be formed. So now we have to calculate the energy that's going to be given out. Firstly, 1 CC bond I can see, so I'm going to write 1 CC bond. Plus I can see 1, 2, 3, 4 CH bonds. I hope you guys can see it. 1, 2, 3, 4 CH bonds. 4 CH bonds. Plus I can see 2 CF bonds. So there are 2 CF bonds as well. Plus I can see 2 HF bonds. 2 HF bonds. Okay? So now I'm gonna replace all the CCFF with proper wordings, proper numerical values. Okay? CC is gonna be 350, so it's gonna be 1 times 350. Then 4 CH bonds, so it's gonna be plus 4 times 410 plus 2 CF bonds. So I'm gonna write 2 CF bonds, I'm gonna write X for it. And then plus there are 2 HF bonds. 2 HF bonds. I'm not given with the value of CF bonds. You can see it in the table. There are no CF bond. I have to find it out. So I just, instead of CF bond, I wrote 2X. Okay, and now HF bonds. 2 times HF bonds, which is 5, 6, 2. And now you just have to plug in all these values into your calculator, which is 350 plus 4 times 410 plus 2 times 562, and that gives me 3114 plus 2x. 3114 plus 2x. So that's my all the energy that's going to be required to to make. Okay, so now what I do, now you know what to do. Energy given in and energy taken out. So energy that was given in was 3126. This was the energy that was absorbed, this energy. And you subtract from it energy that was released. It was 3114 plus 2x. Okay, and now if you solve this expression, it is and the enthalpy change comes out to be, when you solve this, you'll get the enthalpy change, and the value of the enthalpy change is negative 960, equals to, this entire thing will be equal to negative 960. Okay, so 3126 minus 3114 plus 2x equals to negative 960. Okay, 2x equals to negative 960 plus 3114 minus 3126. 2x equals to, let's see what it comes out to be, negative 960 plus 3114 minus 3126. Negative 960 plus 3114. So it's negative 972. X is going to be equals to negative 972 divided by 2, which comes out to be 486, negative 486. Now the negative sign just tells you that the bond is being formed. Negative, because over here we were forming a bond, so the negative signs tell you bond is being formed. So it's going to be a 486. Negative, positive means the same bond is being broken. Negative value means simple, this is a CH bond. If the bond is being broken, if I break it, the enthalpy is going to be positive 486. And if I form this bond, it's going to be negative 486. So the sign of the enthalpy depends on either bond is being formed or broken. So it's going to be option number C, and that's it for today's class. I hope you liked it, and do consider subscribing to the channel. That's going to mean a lot.